Thank you very much. So good afternoon, everyone. My name is Victoria, and today we are going to discuss my PhD work, which is entitled Wake Dynamics and Betatron Radiation in Beam-Driven Plasma Acceleration. And I've divided my presentation into three main parts. We will start with the introduction. I will tell you about plasma wake field acceleration, about its standard bubble regime, and why we need to use plasma accelerators. What is the motivation for this? Then we will move to the second part, which is going to be about betatron radiation. And I will show you some experimental results which we have obtained in SLAC. So this is Stanford Linear Accelerator Center. And I was participating in data taking, and I will show the result and interpret them. And finally, we will talk about another interesting regime in plasma, which is called wakeless regime. And we will see if it's possible to switch between these two regimes in the experiment. Okay. So you know that plasma consists of separated charges. We have positive ions and negative electrons. If you select large volume, the net charge inside is going to be 0. So the plasma is quasi-neutral. And imagine in such a plasma, we have an electron bunch which propagates. And due to its negative charge, the plasma electrons are going to push away from the propagation axis. And ions stay mostly motionless because of their big mass. However, due to transverse force of ions, electrons are going back, cross the axis, and finally close the cavity. So we have the formation of the bubble. Then the process repeats, and we have plasma oscillations. So a good analogy for this is a surfer. So imagine you have a boat which travels through water. It produces a wake behind it, and we can accelerate the wake surfer on this wake. So this is an analogy for plasma wake field acceleration. So why do we need plasma accelerators? We already have conventional accelerators. However, the conventional accelerators are limited because of the metallic structures. So we can have a breakdown of the metallic structure, and that's why we cannot go higher than a particular electric field. And the limit for this field is 100 megavolt per meter. However, in plasma, we can have much higher electric fields, 1,000 more. And this is up to 1 gigavolt per meter. So we can have shorter distances for the same energy gain. And during the last 20 years, the plasma accelerators were developed rapidly, and already accelerating gradients up to 50 or 100 gigavolt per meter were demonstrated. Okay. Now I would like to show you a 3D visualization of the standard so-called bubble regime in plasma acceleration. Here you see plasma electron density map, and I obtained this image with my own code, which I have developed in the beginning of my PhD track. And here with the red arrow, you see the position of the driver. So the driver propagates in plasma, and it creates the bubbles behind it, and at the rear of this bubble we can put a second bunch which is called trailing bunch or witness bunch, and we can accelerate this bunch. This position is very favorable for electron acceleration because here is going to be focused and also to be accelerated. However, if we think about global goals, and for example about building a linear collider, plasma-based linear collider, we need to accelerate not only electrons, but also positrons. And here you see a possible scheme for future linear collider, which is based on plasma wake field acceleration. On the left side, we can accelerate electrons. On the right side, we can accelerate positrons. And finally, we need to collide them. However, it's not possible to get energy gain about 1 tera-electron volt just per single plasma stage. So in the future, when we need to build a linear collider, we will use several PW phase stages. And at every stage, we can get some energy gain, and we need to repeat. However, it's a long path. It's not easy, and we need to synchronize all these stages. And as I mentioned, we need positron acceleration as well. So today, at some parts, I will talk also about positron acceleration. When we accelerate particles, we need not only to have huge energy gain, such a multi-GeV energy gain, but also to be efficient. And one of the important parameters is the energy transfer efficiency. In simple words, it's the energy obtained by witness divided by energy of the driver. So the more we can transfer, then more efficient we are. Another important parameter is the geometric emittance. This is defined with this formula where x is the particle position and x prime is the angle. And in simple words, it's just the size of the beam multiplied by the divergence angle. So the smaller we have it, the better the quality of the beam. But when we accelerate the beam, geometric emittance changes. And it's not going to describe the quality of the beam. So usually people use something similar, but a bit different, which is called normalized emittance. And if we have some optimal conditions, this normalized emittance is going to be constant, and then we can understand if the quality of the beam doesn't degrade. So to summarize, when we accelerate particles, we need to have huge energy gain, at least multi-GeV. We need to have low emittance, because it's linked to the beam quality. We need to have high energy transfer efficiency, more than 30%, and we would like to have low energy distribution inside the beam, so the energy spread should be below than 1%. And for now, I would like to show you some results which were already achieved in electron acceleration. So you understand that things that we discussed, it's not just theoretically, it's practically, and some good achievements were already demonstrated in different labs. And the first result is from flash forward, and here they were able to accelerate the trailing bunch with plus 40 mega electron volt energy gain. It's not the huge number itself, however, they had good parameters in terms of energy transfer efficiency and energy spread. And another important result which I would like to show was obtained in Stanford Linear Accelerator Center during Facet 2 campaign, in which I was participating in person. And here you see a huge energy gain, which is 6 giga-electron volts. So the initial energy of the beam was 10, and finally we have 16. So it's really a good achievement. So we now understand that in electron acceleration we already have a lot of results, and it's good. Okay, I would like to finish for the introduction part and move to betatron radiation. So let me explain what is betatron radiation. Imagine, again, electron beam propagates in an ion cavity, and due to transverse forces of ions, the electrons in the beam start to oscillate. And when they oscillate, they emit radiation. And this radiation is called betatron radiation. So the specific characteristic of this radiation is its spectra, and this spectra reminds us the synchrotron-shaped spectra. So you see it here. And there is a specific parameter, the characteristic energy, which is called critical energy. So with this critical energy, we can understand energy of photons which were emitted during these oscillations. And also the critical energy of these photons related to the amplitude of these oscillations. So in this formula, you see x0 is the amplitude of betatron oscillation, and EC is the critical energy. And this betatron radiation measurement is an interesting tool which can tell us about things which are going in plasma. And I will explain you why. So when beam propagates in plasma, it could stay with the same size, and it could change its size during the propagation. So we say that the conditions are optimal, or beam is matched when it propagates, and the size of the beam stays the same. So here, with this plot, you see with the blue line the RMS radius of the beam. And you see here during the propagation, it stays approximately the same. And emittance here it's normalized emittance, also doesn't change. So it means we are matched. However, in a different situation, when conditions are not optimal, the size of the beam is going to oscillate, and when particles oscillate more, they emit more, and we also see that the emittance is growing. So in this case, we say we are mismatched. And there is a formula which links the normalized emission emittance to the size of the beam, to its energy, the gamma factor, and to the plasma density. So when everything is good, we are matched, and the radius of the beam stays the same. And how it's related to betatron radiation, because we are talking about betatron radiation. So with the simulation, at earlier research at LAA, it was found out that if we minimize radiated energy during the experiment, we automatically minimize the emittance growth. So if we change the trailing focal plane position, we basically change the relationship between these parameters. And when we are matched, we have low radiated energy, and we don't have change in the emittance. So it means that even without measuring the emittance in the experiment, which is a difficult thing, we can just measure the radiated energy, we can minimize it, and in this case, we automatically minimize the emittance. So betatron radiation is a very powerful tool, and it's not destructive diagnostics. Okay. Now I would like to tell you about E300 experiment at Facet 2 at Stanford Linear Accelerator Center. And this was the main experimental campaign in which I was participating. So let me tell about the goals of this experiment. So basically, this is the name of the experiment, and it already contains the goals inside. In SLAC, at Facet 2, we usually have the initial energy of the bunch equal to 10 GeV. And the goal of this experiment is to multiply this energy by 2, so end up with 20 GeV. Another important thing, again, it's energy transfer efficiency. So as I told you, we would like to have high efficiency, and it means we would like to have more than 40% of efficiency, and we would like to have a low energy spread of the accelerated beam. And the final goal is the minimizing the emittance, because it's linked to the quality of the beam. And as I told you, there is a correlation between the betatron radiation level and the emittance growth. So we are going to measure the betatron radiation. Now I would like to show you in more details how Facet 2 is constructed. So you see, here you see the part of the accelerator. Here we have an electron source, and it sends the beam with energy of 10 GeV and the charge of 1.6 nanocoulomb to a sequence of bunch compressors, so we can shape beam. And finally, it arrives to the experimental area where we have plasma, so it's going to propagate through plasma. And after this experimental area, we have a diagnostics table, which is represented here, and it includes different cameras, different detectors. And for now, we will be interested in particular in gamma 1 and gamma 2 detector, because they are measuring the betatron radiation. Gamma 1 provides information about the integrated radiated energy and its angular distribution. And before the gamma 2, we have this small thing, which is called material set, or I will call it sometimes camembert. So we have a set of different materials with different thicknesses. And these materials will help us to understand what was the spectrum of this radiation. And I will tell you later in more details why. Also, I would like to notice that experiment E300 was operated in a self-ionized gas. Depending on the shift, we use or hydrogen or lithium vapor, because they are easier to ionize. Okay, let's move. And I would like to show the data which we obtained with gamma 1 and gamma 2 cameras for different pressures. This is data from 2022, and this was the first touch for me with this experimental data. And I wasn't participating yet at that time in the data taking, but I was already participating in the data analysis. So here you see the angular distribution with gamma 1, and we go from the left to the right, and pressure is increasing. So we start with low pressure, and then we have higher pressure. Here you see the sectorized images. They are from gamma 2, so each sector corresponds to different material with different thicknesses. And you see that when the pressure is increasing, the signal on gamma 1 is increasing, and we also see much more difference in gamma 2. So it means that probably beam interacts more with plasma because we have more radiation. And this is confirmed with electron data. So what you see here, it's the distribution of energies in the beam after it passes through plasma. And here you see a huge deceleration of the driver beam. So it means we had a huge interaction. And yes, in this case, we see higher radiation level. So it's reasonable. Okay. Now I would like to tell you a little bit more how the materials with different thicknesses allow us to understand what was the spectrum of the radiation. So again, each triangle is a different material with different thicknesses. And when radiation passes through these materials, they respond differently. So each material has own response function. And that's why the level of the signal behind these materials are different. So if we compare the signals, we can understand and reconstruct what was the radiation. But to do this, we need to know what are the response functions of these materials. And here it is. I obtained these response functions with a simulation tool, which is called GEAN4. Basically, it propagates the particles through different accelerator parts and repeats the real process. And finally, it detects what was the particle distribution after the detector. So we can get these response functions. Vertical axis is the deposited energy fraction, and the horizontal axis, the incident photon energy. And we see an interesting behavior here. When we go with energies up to 1 mega electron volt, the materials work as filters. So it means if we have a CK filter, the low energy signal will be recorded behind. If we have a thin filter, we will have higher signal. This is happening for the energies up to 1 MeV. However, if we are going to this part and photons have energies more than 1 mega electron volt, we see the change in the behavior. So in this case, we say that materials work as converters. And it means that for thin filter, we will have lower signal than for the thick filter because the production of secondary particles. So these secondary particles increase the level of the signal. But for energies, we had at facet 2, it was below than 1 mega electron volt. Usually it's X-ray range like from 10 to 100 kilo electron volt. So we work in filter mode. And sometimes I will tell you that we use a filter set. So this is the material set. Okay, so how we are going to reconstruct the spectra which we had during the experiment. We have this measured signal behind the triangles. We have these response functions. And what we are going to do? We suppose that the radiation spectra of betatron radiation is the synchrotron. So if I basically multiply synchrotron spectrum by response function, I should get the predicted signals. But I need to vary the critical energy of the synchrotron to fit my experimental data. So I do a scan of different critical energies. I multiply spectrum with this critical energy by the response functions, and I compare the theoretical predictions with the real experimental signals we had. And here's the result. So what you see here, you have a dashed line here. This is predicted theoretical signals if we use synchrotron approximation. And this was fit with 65 kilo electron volt. So you see it's data for different materials with different thicknesses. And yellow dots is the experimental signals. And what we can notice that for tungsten, the agreement is quite good. And for copper, we see there is a disagreement. And also, what is weird, that the signal behind copper 1 millimeter is higher than behind copper 0.5 millimeter. So it's surprising. And basically for another pressure, for another critical energy, we also had this problem with copper. And at this point, we started to think maybe copper has some corrosion because you know it's placed inside the accelerator. There is a lot of radiation, so maybe there is a corrosion. And at this point, we decided that we need to replace the material set and see if it helps. Also, you maybe have a question why I have two dashed lines here. Actually, I did fit for normal synchrotron with one critical energy which stays constant. And I also used generalized synchrotron function which accounts for deceleration and different critical energies during the propagation. However, you see the difference is not huge, and therefore, in later analysis, I just used normal synchrotron function with one critical energy. So, okay, again, we identified some problems. We have disagreement for copper, so maybe we need to replace the filters. And we need to check theoretical approach, because maybe synchrotron description is not good enough. And now we are moving to new stage of experimental campaign. And starting 2023, I was participating in experiments in SLAC in person. And for the whole year, we were not able to obtain good data. And here I have an example from spring 2024. You see, it's very bad data. Actually, the camera was dying mostly. And we couldn't even record anything. But when we were able to record the data, it looked like this. So we had a lot of noise. We also had this parasitic radiation. And it was not possible to calculate the betatron signal. And in autumn 2024, we had a huge upgrade. So the first upgrade is two-beam operation. The data which I showed you before from 2022, they were for single bunch. So we only had a driver, and we recorded the radiation from the driver. But as I told you, we need to know the radiation from the trailing bunch, from the witness, because we are going to use this match condition and minimize the emittance growth. So we need to record radiation from the witness. And that's why we finally started to operate in two beams. And here you just see the image from the spectrometer, which demonstrates that the second beam, which is witness beam, was accelerated. So initial energy for both is 10 GeV. And then with this projection, we see that after some propagation, witness has 10.5. So we have acceleration of witness bunch, so we can confirm we have two beams in the experiment and there is some acceleration of the witness beam. So also we replaced the material set. So I prepared a new camembert. I was designing, cutting this, and finally putting all things together. So we updated the copper material, and we also got a new scientific camera which had much higher dynamic range, and it helped finally to record good data. Okay, a little bit more about two-beam operation. So when we run the experiment, we usually do some scans. And here we have a scan sorted by bunch separation. So we have a distance between the driver and the witness, and we can change this distance and see which positions are more favorable for witness acceleration. Okay, and with this energy axis, we can see what was the energy of the witness after acceleration. So for every single shot, you see what was the bunch separation and what was the final energy of the witness. And for my betatron analysis, I can only select a small range of the energies, because I don't want to have too much different critical energies in my betatron radiation. So for example, if I will use a shot where witness was accelerated by 0.5 GeV and then a shot when witness was accelerated by 5 GeV, it's going to give us different results, different critical energies. That's why I only select the small range, for example, with 1 GeV energy, to analyze what was betatron radiation from the witness. And one thing to say is it's not possible to measure directly the witness radiation, because or we have just driver or we have driver plus witness. We cannot have a witness without driver because it's not going to be accelerated. So to extract the signal from the witness, we need to do two measurements. The first measurement is when witness is blocked and we have only driver. So this is gamma 2 image, so you can recognize these sectors, different materials. And then we unblock witness and measure the radiation from two beams. And what you already can see is that the signal here is higher than here. So it means the radiation obtained from the witness, it's not just noise, it's recognizable radiation. So we are very happy at this point because we're finally able to measure the trailing bunch radiation. And it means that in future, if we can minimize it, we basically minimize the emittance growth. Okay, here you see even more results. Here you see also angular distribution. So this is gamma 1 analogy, but now we use just one camera and we basically use a motor to move filters out and filters in. And when filters are in, it's gamma 2. And when filters are out, it's basically gamma 1, so angular distribution. So what we do, we subtract the signal from driver plus witness and finally obtain just witness signal. So we can distinguish two signals from the driver and from the witness. And you see the final image which obtained after normalization. And each color corresponds to different signal levels. So here you can understand, for example, that red is high signal and blue is low signal. Okay, so we have this data, and we can repeat the analysis which I did for 2022. And here what we have. So general behavior is not that bad, because now you see that for copper, for example, it's logical that for copper 1 millimeter we have lower signal than for copper 0.5. However, still the fit is not converging to the real experimental signals. So we still see some difference, and the dashed line doesn't repeat the experimental signals. You have separate fits for witness beam and for the driver beam. However, with the energy resolution I had, it was the same fit, but we can notice that I think for the witness, the signal is basically higher, and it's not going to be 45, it's just the limit of the scan, but probably for witness we have like 2 or 3 kilo electron volt higher energy. So we see still the problem in fitting, and again we need to think why it happens. So the first very simple idea, maybe synchrotron approximation is not working. So we need to check that we can describe our data with synchrotron approximation. And for this, I'm going to produce synthetic data with a simulation and check if for simulated data, the synchrotron description is good enough. Another thing, which is going to be more complicated, it's that maybe in the experiment we had some non-uniform low energy photons. And that's why finally we have fit which is lower than the real critical energy of betatron radiation. Also, there are some secondary suspects that maybe filter response are non-ideal, maybe the thicknesses of the materials are not homogeneous, but it's not going to change our data by 20%. So probably there is something we really not yet understand. Okay, but the thing which we can check, the simple thing, is the synchrotron approximation. So I'm going to produce synthetic data, exactly the same that in the experiment, and check if for them the synchrotron approximation is working. So this is the whole multi-tool chain, and I start with LINAC-Lucretia simulations. So Lucretia is a code which was developed in Slack, and it propagates the particles in the accelerator. And finally, it allows to get realistic phase space distribution at the plasma entrance. So I can get an input beam for my simulation. Then once I have these beam distributions, I go to peak simulations. And in my work, I used 3D quasi-static peak code, which is called HiPace. It was developed in DAISY. And due to this code, I can propagate the input beam and record trajectories, which you see here. So once I have these trajectories, I can calculate the radiation. And for this, I used Syncrat code. This is based on Lienard-Wiechert potentials. And Syncrat was developed at LA, and it allows us to get the spectra of the radiation. So here you see synthetic gamma-1 analogy. It's angular distribution of the radiation we had. And here you see the integrated radiation spectrum, so you can recognize the synchrotron shape, and we can get the critical energy with this result. So, okay, and once I have these radiation measurements, I can do the same fitting. I can use, again, synchrotron with a specific critical energy. I can scan these energies and see if theoretical description and predicted synthetic data signals are the same. And the answer is yes. So for synthetic data, the synchrotron description works very well. We don't have disagreement for any filter. So for copper, it's also very good. It means that problem is not in the synchrotron approximation. It's something else. It's something in the experiment, and it's a very difficult thing because we still don't understand what is the reason. Okay, I would like to conclude for the betatron part. So as I told you, this is a very promising complementary non-destructive diagnostic for beam dynamics. And during Facet 2 campaign, we were able to measure the radiation signal from trailing bunch only. And this is very good achievement, because if we can control radiated energy from the trailing bunch, we can minimize the emittance growth. So as for me, it was a long path. I was participating in several E300 shifts in person at SLAC. I started with the analysis of 2022 data, then I continued with analysis of 2024 data. So I did this multi-tool simulation chain, and I did some checks if we are going good or not. So this is all for this part, and I'm going to move to the third part, which is about different regimes in plasma acceleration. So in the first part, I already told you what is standard plasma wake field acceleration, the bubble mode. So usually we have large size of plasma, so the bubble inside this plasma can form, and we can accelerate particles in these bubbles. But there is another mode, which is called wakeless. And imagine that now we reduce the size of the plasma. So we try to make plasma smaller than supposed size of the bubble. So it means that when electrons are going away, they could not return, and they are not closing the cavity, and we don't have the bubble anymore. And in this wakeless mode, we don't have much longitudinal electric field, so we are not going to have acceleration with this mode. But because here we have an ion channel, it's going to be focusing for an electron bunch. And it means that the wakeless regime could be used as a good thing for betatron radiation source, for beam transport, because it's going to focus beam and doesn't change the energy of the beam too much, and also as a base for ion channel laser. Another interesting thing is the transition regime between two. So we can have standard bubble regime, we can have wakeless mode, but what is in the middle? In the middle, we have a mode which could be good for positron acceleration. So as I told you in the beginning, for the collider we need also positrons, and that's why we are talking about positron acceleration. So when electrons are going back to the axis, they hit the axis at different longitudinal positions. And now the area where we can put a trailing positron bunch is extended. So in this area, when we have electrons, we are going to have focusing for positron bunch, and it's also going to be accelerated. So the question is, can we control the mode switching in the experiment? And for example, in the same run, we have plasma wake field acceleration standard bubble mode, and then we would like to have wakeless mode. Or we have to, or we would like to have the transition mode. So can we somehow switch between these different regimes and get some benefits? And the answer is yes. And the first investigation of this regime switching was done at Facet 1. So it's an older campaign. And in Facet 1, they used different gas fields. So they started with pure helium. And helium is very hard to ionize. Here you see the ionization potential of helium. And then they started to add a little bit of argon and change the number of argon and helium. So when we have pure helium, it's hard to ionize. We can ionize only narrow size of the plasma. And in this case, we cannot get bubble regime. We don't have acceleration. So you see there is nothing here. So no energy is higher than the initial energy. And it means that we have wakeless mode. Because here we see some deceleration. So there is an interaction, but we don't see any acceleration. So with pure helium, it's wakeless mode. Then we started to add argon. And you see that we have higher interaction here. So we see more deceleration, but not yet acceleration. And finally, when we have 50-50, helium and argon, we see acceleration here. So it means that we started to be in standard bubble regime. So we have switched the two regimes, and it's good. But it's not very convenient in the experiment change the gas field. So the question is, can we have something more convenient, something easier? And during Facet 2 campaign, we discovered something very interesting. So here you see a scan. It's a lot of shots, and these shots are ordered with a bunch length. So we go from shorter bunches to longer bunches. And you see that for shorter bunches, we have acceleration here. So the vertical axis corresponds to the energy. So the initial energy was 10, and now we see something above 10. So we have something up to 15 GeV. And we have the acceleration, but then we started to change the compression of the beam and got longer bunches. And finally, we see nothing. Like there is no acceleration anymore. However, we see deceleration, so there is an interaction. And at this point, we made a guess. So maybe changing the compression of the beam, we can switch between the two different regimes. And to confirm this, we need to use several tools. The first tool is confirm what we have seen in the experiment. And for this, we are going to use the shadowgraphy method. So there is a scheme for shadowgraphy method here. But in simple words, we use a laser beam to make a shadow of plasma. So we can really see what was density variation in plasma. So we can image these bubbles if we have them. And we have different behavior in shadowgraphy projection. When we have no accelerated charge, so we suppose we are in the wakeless mode. And when we have accelerated charge, so we are in the standard PWFA. So you see much more colors here. And now let's look in more details. So in the cases when we had accelerated charge, the shadowgraphy images looked like this. So you can recognize the bubble structures. So beam is going to the left. So with this star, you can see the position of the beam. And behind this beam, we have the bubbles. We have the plasma waves. So it means we have the standard PWFA. And then when we don't have accelerated charge, what we got with shadowgraphy is here. And it reminds us what we have seen with the 3D visualization of the wakeless mode. And here you can see it even better with bigger size. And I also put the dashed line. So you can recognize this bubble. And here the electrons are crossing the axis. So that's why we have increasing signal here. A lot of electrons going here. And for the wakeless mode, you see again something very similar to the 3D visualization. So we can confirm that in the experiment we had PWFA and wakeless, and not PWFA and nothing. So it was different. It was two different regimes. And another good tool to check is the simulations. And I did a huge simulation scan. So I used an input beam. I send it to the plasma, and I start my simulation when the size of the beam is large enough, so we don't have yet ionization. So it's not focused at the beginning of the simulation. And then when we propagate, we have the waste of the beam, so we start to have ionization. So for my first scans, I used simple Gaussian transverse beams, and I only used longitudinal current profiles from the Lucretia. So as I told you, Lucretia allows us to get some realistic current profiles and the phase space profiles of the beam. So for this simple scan, I found some features which allows us to switch between the two regimes. And then when I understood it, I started to use full 6D beam distributions from Lucretia. And so it's very close to realistic beams. And the only thing I did, it's scaling. And I changed the size of the beam to 10 by 10 microns. This is because sometimes when we use Lucretia inputs, the X size of the beam is too much and we don't have ionization, so that's why I need to scale. However, the distribution is fully 6D, so we are good. And for these 6D simulations, I would like to show you the results. And the results are here. So now you can see that the first beam has this current profile with high peak current. It's almost 70 kilo-ohm, so it's peak compression. And for this beam, we got bubbles. So we have standard PWFA regime. This is the plasma density. Then you have the transverse force. So we see the focusing here, focusing, defocusing regions. We have the longitudinal electric field. So we see the variation in accelerating and decelerating fields. And we also have the energy spectra. So this blue, you see the initial energy spectra. It's just localized around 10 GeV, so the initial energy of the beam. And then we see the distribution of the particles, and the energy is going higher, so we have some acceleration here, so it's PWFA. And when we used another beam, which is overcompressed double horn beam with a moderate current, and peak current was around 20 kilo-ohm, we got the wakeless mode, so you don't see any bubbles here. You see that we have transverse field, which is focusing, and we have low electric field here, low longitudinal electric field, so we don't have much energy change here. Okay, with long path, of course, it's going to decelerate. But in comparison with what we had for PWFA, the value of electric field is lower. So we see only deceleration here, there is no acceleration, and finally we can conclude that yes, by changing beam compression, we can switch between two different regimes, between the standard bubble mode and between the wakeless mode. And now I would like to conclude part 3. So we got an important result, and this result is going to be published, hopefully soon. So we confirmed that changing the compression of the beam during the experiment, we can go from one regime to another. I was participating in data taking, in a huge simulation scan, and finally we have these results. And now I would like to move to general conclusion to finish my speech. So today I didn't mention too much, but actually it's presented in my manuscript. In the beginning of my PhD track, I've also developed a trajectory-based code, which could be a fast alternative to full peak, because it's very quick. You can run it with a simple laptop. And this code allows to have local resolution with a non-uniform refinement. And this code is good for quick study scans. And in the beginning, I showed the 3D visualization of bubbles, so this was performed with this code. And moving to the part which we discussed today, this is betatron radiation and mode switching. So again, to repeat my contribution, during betatron radiation campaign at FACET2, I was participating in different T300 shifts. In data taking, we had a lot of difficulties, and finally we end up with good data which allows us to distinguish the trailing bunch signal. And betatron simulation, and I did the betatron simulation to confirm that we can describe experimental data with synchrotron approximation. And I showed you the multi-tool simulation I used for it. And in terms of regime switching in facet 2, again, I was participating in experiments. I did a huge scan of simulations to confirm that by changing the compression, we can go from one regime to another. And this is the key result of this part. So thank you very much. If you have any questions, I will be glad to answer them.